So this morning I want to finish off this section here. There's just a couple of slides that I want to work my way through on Cognito, which I started talking about the last day. And in terms of labs for this week, this is the lab that you should work your way through. And as I've mentioned to you last week, when you've completed this lab and when you get to start bringing in Cognito into your assignment. If you decide to do that, then you can reuse um, any of the code that I'm providing in this lab. You're free to reuse that in the assignment. So let's go back to this set of slides here. And so the service we were talking about was Cognito. And in short, Cognito is going to provide authentication and authorization functionality or features to our applications. In our case, it's a web application, but to any type of server-side application. The main kind of concept or resource, sorry, that we create when we're using Cognito is what's called a Cognito user pool. And you could think of a Cognito user pool essentially as a database, albeit a serverless database of your users' accounts, plus some additional functionality. The additional functionality is the kind of standard authentication and authorization functionality that you would use in any type of application. We then talked about this architecture for our application, for a web application, and I suggested it's a typical kind of architecture. And what I meant by that was typically you had two web APIs, one web API which was responsible for dealing with all authentication related requests. Hence, it's actually communicating, its backend, if you like, is supported by Cognito. This is representing Cognito. Although as a developer, you have to implement a number of lambdas. So you can imagine, you could visualize there being a number of lambdas here. And essentially each lambda deals with one particular type of authentication stroke authorization request, i.e. sign up, confirm sign up, log in, log out. And we'll have a brief look at these lambdas in this morning's lecture, and I provide the code for them in the lab anyway. So this web API, and this is just a standard web API, and we set it up in the way we know how to set up web APIs. The backend, they're integrated. The web API is integrated with lambdas. We know how to do that. The only difference is that these lambdas here are just communicated with the Cognito service. That's the only thing that distinguishes them from any other type of lambda. The Cognito service is like all other AWS services in that it provides a web API interface, and it comes with an SDK. And so we would use the SDK associated with Cognito in these lambdas, as you'll see. Down here then is a web API, which tends to be the front end for all of our applications' core functionality. And this is more representing the core functionality over here. And we know how the flow of control works. Your client, or could be a React client, or it could be actually a native app like an Android client. It uses this web API to sign up, log in, log out, etc. In terms of CDK stuff, we said the last day that this is the code for creating a Cognito user pool. And for every Cognito user pool, you need to also declare or create a it's actually called a web client really. And so whatever, and it's our lambdas will be using this web client here to communicate with the Cognito service for the purpose of making changes to this particular user pool. Now, my diagram 2 slides back had 2 web APIs. So here's the detail of my 2 web APIs, which we talked about the last day. Down here, I'm just showing you an excerpt from the actual project, and you will have this project completed in this week's lab. And you can see that there are a number of lambdas related to the whole authentication part of our application. And there's a lambda, you can tell from the names of the lambdas what each of these lambdas is responsible for. There are also lambdas, which in my case are these 2 down here. These, Maria, are the lambdas that are associated with implementing some functionality related to my problem domain. Okay, in my case, they're simple lambdas that just return a response. These are the lambdas that we're kind of interested in. And then I gave you a demo of this working in the last day, so I won't go through that again. You can revisit last week's lecture too, if you want to remind yourselves about that. But you'll be working your way through that demo anyway in the lab this week. And so just stepping my way through it again. So this is a screenshot from Postman for a sign-up request. Okay, and in my case, a sign-up request includes a body, and the body includes the user's chosen username, their chosen password, and their chosen email address. When we send that request, we saw the last day that as well as getting a response back, we also get an email message giving us a code. But when I click send on this request here, then that, if I may go back, that request is sent to this web API. The mappings I have for this web API causes it to invoke a particular lambda, right? And the lambda in this case, it looks like this. So this is the lambda that is executed when my top web API, my auth API, receives a sign-up request. And if we just briefly step our way through it at the very top here, you can see we're creating an instance of the Cognito client. So this is the Cognito SDK's client that any Lambda would create an instance of for the purpose of talking to Cognito. And the way we actually communicate with this client, the Cognito client, is quite similar in terms of the coding style anyway. It's very similar to the way we communicate with the DynamoDB SDK client. If you remember, with the DynamoDB SDK client, we create what are called command objects, and we send those command objects to DynamoDB. It's the same kind of pattern that we use with Cognito. With Cognito, we create Cognito-specific command objects, and we send those command objects to the Cognito service. So, for example, there is a sign-up command object. These are the properties of the object. So here we're obviously just extracting the username, password, and email that were included in the body of the request that was sent to my web API and then forwarded on to this particular Lambda. So we're just extracting those. Then we're creating in this case, as I said, a sign-up command instance. This one here, this property here is a reference to the Cognito pool client that we created in our CDK stack. So I might just be allowed to flip back to here, which is this guy here. The other properties then are taken directly off of the requests that were sent by the user. This property here is just telling us that, oh yeah, that's okay. It's just the email part. And then we create an instance of our sign up command and we send it to the Cognito service, essentially. That's what we're doing here. And the response comes back, which is presumably successful. If there's an error, then it throws an exception, and our React client, if let's assuming it's React, our React client has to deal with that. So the flow of control here, I think, is fairly straightforward. We know that there's sign up or registration is a two-step process. The second step is confirming your sign up. And so here I'm showing you a screenshot from the Postman for a confirmation sign up request. Confirmation sign up request includes a body, and the body has two parts to it: the name of the user and the code that was sent to us by Cognito via email. Okay. So when we click send on this request, another Lambda is triggered, and this is what the Lambda looks like. Again, I will give you all this code in this week's lab, but the flow of control is almost identical to the flow of control in the previous Lambda that we looked at. We create an instance of our Cognito SDK client. We extract the relevant data from the request that comes into the auth API. In this case, we create a confirmation sign up command object with properties. And again, we need to include in this object a reference to the Cognito user pool client, the data, and create an actual confirm sign up object instance, send that object to my Cognito user pool via the Cognito client, and hopefully get back a successful response. It may throw an exception. It shouldn't. It would only throw an exception, I guess, if the code, for example, if the code that I had included here, if the code was incorrect, then we would this would throw an exception. Where am I? Sorry, this would here would throw an exception, and it would skip over that, and the catch block would deal with the exception and essentially send back an error message back to our React client. Otherwise, we send back this kind of a response, and that's what we see here. That's what we see here. Okay, so this is all fairly straightforward, I think, I hope. Next is I'm showing you the Lambda that's triggered when a user tries to actually log in or sign in. So at this stage now, we have what we call a confirmed user. Confirmed user is a user that has signed up and also confirmed their sign up request, if you like. The flow of control is similar to before. There isn't a sign in command object. Instead it's called an init auth command. Okay, just a slightly different name. But the flow looks similar to before. So again, we need to refer to the Cognito user pool client in this request. This is just a flag that's telling Cognito the authentication flow style that we're using. Okay, so this is kind of boilerplate, really. And we're including the username and password that the user is sending to be validated. We create an instance of our Cognito object, our initiate auth command instance, and we send it as before. Where are we sending it? We send it. Now, what we get back from Cognito in this case is, okay, it's an object, but within that object, there's a particular key, which is this one here, and it will contain a reference to a cookie. It'll beg your pardon, it'll contain a reference to a JWT token that Cognito has created dynamically for me. And if I just go back, if I go forward, we saw what the token looked like the last day. And you're familiar with JWT tokens anyway from the web app dev module. So all I'm doing here between these two lines is I'm extracting the actual token itself, which is just a big long string. So this variable here is going to refer to the JWT token. And in the response, and this is just the way I decided to do it, in the response that I'm sending back to let's say my React client, I'm including a response cookie header. And the cookie header is assigned a string. And the string is just a set of key value pairs in stringified form. Now, in my case, there's only one cookie in this string, but there could be more than one. And my cookie string looks like this. I did say it's a set of key value pairs, so I decided that the key that I'm going to use is called token, and the value is the actual JWT token string itself. Okay. Now I'm also including, for no good reason, I'm including the actual token in the body of the response. That's what I'm doing down here. That probably wouldn't be a good idea in general because it could be hacked. Okay. But by including it as a cookie header rather than in the response body as a cookie header, and this flag over here, I don't want to get into it, but this is a special kind of flag that you set, which will disable hackers potentially getting at your cookies. Okay, you can read up on this yourselves. I don't really need you to be informed about it, but so if we kind of ignore the fact that I am actually sending the cookie in the body of the response, for now, when I'm sending the cookie in as a sorry, I'm mixing up my terms now. Sorry. Ignore the fact that I'm sending the JWT token in the body of the response. And let's concentrate on the fact that I'm sending the token as a cookie response header. Then that means I need to be able to extract the token from the cookies that are sent by my server side back to my client. And I showed you how to do that the last day. If I go back to, let's see, the back and forward to this slide here, you saw how I did it the last day by clicking this here. When you click that, you're given you can see all of the cookies that were sent by the server side to you, where each cookie is a key value pair. In my case, there is only one cookie, where the key of the cookie is token and the value is a JWT token. Right, so if I go back to the Lambda, I guess, yeah, so that explains what's happening here. What's next? All I'm showing you on this screen here is that there's an online website that you can use and called the JWT.io website. And it's just a nice tool, I suppose. What it allows you to do is if you paste in a JWT token on the left, you may have come across this website before. If you paste in a JWT token on the left, then what it will do is it will decode it and it'll show you what the actual token, what information the token contains. And I'm highlighting here that in my case, the token will contain the username of the user that this token was issued to. And my user was called user A, I think, wasn't it? And we can see that that's included here. And that's really what Cognito service uses as well to determine whether this token on the left is a valid token or not. You know, it'll decode it. It'll then look inside it for the username of the user and then you'll then check the user pool to see is that user in the user pool. And if they are, then it's happy that this is a valid token. So that's the login part of our auth API. So I've showed you excerpts from the lambdas, for most of the lambdas here. There's one or two other ones as well. I call a sign out one, which is trivial really. And at this stage now, my client over here now has a token issued by Cognito. And this token it can use to access protected resources over here. In my case, it will be protected lambdas over here. So we now need to switch our focus down to this web API. Again, it's a standard web API. It has integrations with lambdas here, but it has this other special lambda here, which is going to play the role of what we call the authorizer. And what the authoriser's purpose is, when a request comes in with a JWT token, the web API will essentially pass that token to this lambda, and it will communicate with Cognito to ensure that it's a valid token. If it is a valid token, it will kind of tell the web API that you can forward on the request to the lambda that's over here. Alternatively, it'll say that it should deny access, and there'll be an appropriate error sent back to your client. So in terms of looking at this web API, in my case, there are only two lambdas here that provide functionality. Okay, but obviously this lambda needs to be somehow woven into the way we set this up. So this is the code that's relevant, excerpts of it anyway. So I'm creating an empty web API. I am creating two endpoints to my web API. These endpoints relate to what's going on over here. Two endpoints. I'm creating two Lambda functions. These lambdas, Maria, represent the functionality that's over here. We're not interested in the detail of them. They're just standard lambdas. I am creating a third lambda. It's a standard lambda in the way I created anyway. But this lambda here now is going to be this one here. And so I need to do some extra work to make this lambda play the role of my my authorizer. And so from a CDK point of view, this is what's going on here. You have to create an instance of what the CDK calls a request authorizer. So it's just a new L2 construct. And you can see what I'm giving it here are, I guess you would call it configuration settings for this new L2 construct, this request authorizer. The purpose of the first property here is to tell the request authorizer where it can find the token that is included in a request. Okay, I'm sorry now for flicking back and forth, but this lambda here needs to know how are tokens included in the requests that come along here. And in my case, the token will be sent as a cookie. And that's essentially what this setting is telling the request authorizer. You'll find the token in the cookie headers, the request cookie headers. The other part, I'm just referring to the Lambda function that's up here, because so that's the implementation. And I'm telling it don't cache any tokens. Okay, that's fine. This code down here then is the normal kind of code that you need to do in order to, because if I go back up here, right, I've created two endpoints here, but I haven't integrated the endpoints with any backend, if you like. And that's all I'm doing down here. But we've seen this kind of stuff before, but there's one additional little piece of configuration. So here I'm adding a new endpoint or a new resource to my web API. It's for HTTP GET requests. It's going to be integrated with a backend Lambda. The Lambda is the Lambda is one of the two Lambdas that I've defined at the top here. But what's new is these two parts here. I'm indicating in my web API configuration that this particular endpoint, if you like, is a protected or private endpoint. And so I'm configuring the nature of the authorization that needs to be carried out. And I'm essentially referring to the request authorizer that I've defined here. That's what's going on here. And okay, it's custom authorizer type. There are other types as well. So this bit here now is where I essentially connect this request authorizer with my web API configuration. This is the other endpoint in my web API, but it doesn't have anything special. Okay. This one here doesn't have any of this stuff here, which means that a GET request to this endpoint, and if you look up here, it's the public path endpoint. A GET request to that endpoint can go straight through to the Lambda on the right-hand side. So requests to that endpoint can just go straight through. There's no need to consult with the authorizer. Now, the authorizer code I've given you in the lab, and I've kind of consciously decided not to step through it here. You can just lift it. You can look through the code yourself for sure. All I've done in the slides is to explain the sequence of steps that this Lambda performs. And I just maybe felt that that's as much detail as you need. So is that what I have? Yeah, that's really all I'm documenting here. This is the kind of procedure that the authorizer Lambda performs. Like the first thing it has to do is it has to actually extract the token from the cookie headers. Now, in general, there could be more than one cookie in the cookie header that comes with a HTTP request. The HTTP request cookie header, which is a bit of a mouthful. Okay, this thing here, it's going to be a long string, but the string, when it's parsed, is going to be a set of key value pairs. In our case, the string is only going to have one key value pair, where the key is going to be token and the value will be our JWT token. But in general, it could be a number. So what I'm doing in the code is I'm parsing this header and I'm putting it into a local map structure. And we know a map is a set of key value pairs. Now, in this map, I'm only interested in one of the cookies, or sorry, the authorizer Lambda is only interested in one of the entries in this map, and it's the entry that has the key token. So it looks inside the map to see, is there an entry in the map that has the key token? Of course, if there isn't, then it's clearly an invalid request. So it checks to see, is there one in there? If there isn't one in there, then the way it tells the web API that you should deny access to the backend Lambda, the way it does it is it creates an IAM policy on the fly. I might just show you that for a second. All right, I have the code here. There's a lot going on here now, admittedly, but if I look at the authorizer, is it there? Is it? Let's see, it might be down in the utils. Yeah, so this little function here, create policy, creates an IAM policy on the fly. And so a policy looks like that. So the piece of code that I highlighted there now, that's okay, admittedly a very bare bones IAM policy, but what the policy is telling whoever receives this policy is to, let's see, it's saying to, what is it saying? Oh, it's generic actually. Because this function is called, let's see where it's called from, create policy. Yeah, you see, it's called, and it's either called with a deny. Second argument is either deny or where's the other one? Deny or allow. So okay, so the second argument is either the string deny or the string allow. And if we go back to our create, so this, I said this is the structure of a policy. So this here will be either deny or allow, which is a standard IAM statement indicating to allow whoever receives this policy to either allow them or deny them to carry out this operation. And the operation that I've highlighted there is the ability to execute the web API, to invoke the web API. So if I go back to here, actually, now I was slightly inaccurate, uh, but it was okay for me to say it at the time. But in fact, what actually happens is this lambda here, it's actually executed, if you like, before the request gets as far as the web API. Okay. And so the lambda will either allow the request that comes in from here to invoke the web API or not. And if the request is allowed to invoke the web API, then that means it's allowed to access the lambda over here. If it's not allowed, then it's prevented, okay? And it would be prevented if the token is missing or if the token is invalid. So strictly speaking, this actually executes before the request gets as far as the web API. When I was explaining it earlier on, I said the web API consults with this. It's kind of marginal, really. Maybe it's a two-phase thing, that the first phase of invoking a web API, first phase is to consult with the Lambda, and then whether it invokes the second phase of the web API or not depends on whether this Lambda returns a policy, an IAM policy that allows the second part of the web API to be invoked or not. Either way, all I want to try and get across is that its IAM is used as a means for telling the web API whether a request should be forwarded on to the backend or not. And from those of you that have studied AWS before, we know that IAM is all about security. And this is a very much a security related aspect to our application. Okay. So it checks, first of all, to see, is there a token in the cookie? If there isn't, then return an IAM policy that denies access to the rest of the flow of control, if you like. If there is a token, then verify the token. And I showed you on the website there, I showed you verification means decode it and then check to see is the user's name that's included in the token, is it one of the users that's in my user pool? So, and I'm using a third-party library to do that for me. Now, that third-party library will either return a success or failure, and it's the same thing as before. If it's a successful verification, then my authorizer returns an IAM policy that allows the user's request to be forwarded on. Otherwise, it returns a policy that denies it. Okay. That is that, I think. So that's how I go back to here. Let's just clean up that a little bit. That's my kind of explanation as to how this part here works. Now, obviously I'd like you to understand that, but if from an assignment point of view, all you've got to do is understand this, sorry now for flicking back and forth. Understand this part here, understand that at the CDK level, how to configure it at the CDK level, because I'm providing you with the authorizer implementation and you don't have to go near that. You will not have to make any changes to it. Okay, as usual, I'll pause, but there may be a question, but I don't expect you to have questions, maybe. Any questions? No. Okay, walk your way through the lab, and you may have questions then. Now, there's something else I want to just go back to, if you like, but it's the reason I'm going back to it is because it may be relevant to the assignment. So what I'm looking at here is, I think it's kind of essentially the solution to last week's lab. And I'm particularly interested in, let's bring up the CDK code itself. I'm interested in this stuff here, right? And we know what the purpose of the code that I've highlighted there is. It's got to do with allowing my lambdas to communicate with the DynamoDB service for the purpose of accessing tables. Now, they're nice, convenient functions, but what if there wasn't these convenient functions available to me? How would we kind of manually implement the security that these convenient functions implement for us? Let's first of all look at what these functions actually do behind the scenes. So I want to look at let's say I want to look at the get all movies lambda. Now I've deployed this stack earlier on for convenience. And so if I go to the lambda service, which I'm at here, and if I find the particular lambda that I'm interested in, which is this one here, and I have talked to you before about lambdas and the whole security side of lambdas. And what I said is that a lambda has what's called an execution role associated with it, which we can see here. Okay, execution role. And for each lambda has its own personal execution role defined for it. That's the way the CDK works, but it's based on best practice. Each lambda should have its own IAM policy that implements the execution role. Again, remember the purpose of the execution role is to indicate what other services a Lambda, this particular Lambda, can interact with or can invoke. Now, in the case of this get all movies, well, let's look at its role implementation. Now, when I click this, I suddenly switch over to the IAM service, which is the service that handles all security related stuff in AWS, as you know. And in fact, can I go back for a second? Sorry. Yeah, let's go back to here. Sorry. We get a certain amount of information even at the Lambda service by virtue of this drop-down menu here. This drop-down menu will show me all of the other services that this Lambda communicates with. And in my case, it's two, CloudWatch and DynamoDB. And I'm particularly interested in the DynamoDB. The DynamoDB one is there because of these kind of statements that we have in our CDK, which I think I've kind of outlined before to you. But if I drill down into the role, so here's the role, and I want to look at what's called the policy attached to this role. And we can see that there are two policies attached to this role. This was all generated for us by the CDK. I'm interested in this policy here. This policy was actually generated by the CDK at deployment time. And if I click through to that, am I looking at the right one? Yeah, I am. And so here it's actually showing me the policy, and these IAM policies, as some of you know, you actually code them up in JSON form. That's what the AWS platform understands. So this policy here that you are looking at was generated by the CDK when I did my deployment as a result of these statements here. And if we pick out the ones in particular, this one, okay? And when we look at the policy, surprise, surprise, it's all about allowing access to particular endpoints in my DynamoDB API. And all of the endpoints relate to kind of read operations. Now, okay, there are the actions. Sorry, let me just where does it say allow? Oh yeah. So it's allowing any of these DynamoDB actions to be executed by my Lambda, to be performed by my Lambda on this particular resource. And the resource is the full identifier for, in this case, the movies table. Okay. It's called its ARN, it's Amazon resource number, but it's essentially kind of an identifier. So where am I going with this? Well, where I'm going with it is, supposing we didn't have these convenient methods, this method available to us. So if I comment this out, can I achieve the same result? And the answer is yes, you can. And the way you do it is you actually have to implement the IAM policy in CDK and attach that policy to the execution role of the Lambda. And that's what I'm doing here. And the ability to implement IAM policies in CDK, in the CDK stack, and attach those policies to roles, etc., etc. That may be something that will be useful to you in the assignment. But let's stick with this one. So I've disabled this line here. And when I looked at the detail of that policy, this policy here, it's kind of over provisioned in that it's allowing my Lambda service to perform operations that it doesn't actually perform at all. It only performs a subset of these. So I essentially just took this, copied this, and pasted it here. And I also just removed the ones that aren't actually that I know that are not being used by my Lambda. And in fact, I've narrowed it down to three. But if I kept poking around with it a little bit, it probably only uses, I'd say, this one here. It doesn't actually use the other two APIs endpoints of my DynamoDB service. But this is good enough for now. So I have now commented out this line. I've added in this code. And when I do a CDK deploy and look at the DynamoDB, look at the IAM policy again, then the policy I should see will be very similar to this, but it won't have as many endpoints included in the list. It'll only have three. The other thing in my policy that I've coded up here is, let's see, I have here I'm referring to the what I call the identifier of the particular DynamoDB table, i.e. the resource that these actions can be carried out on. And it's the movies table ARN. ARN again stands for Amazon resource number. It's just a unique identifier. Okay, so let's save the changes and let's do a CDK deploy again. And while that's working its way through, I'm just going to go back to my Lambda. Now I am conscious of the fact that some of you have done some AWS stuff before, some of you have not, particularly the Nanjing students have not. So that's why I'm stepping through this probably too slowly for the Irish students, but that's okay. So it's deployed. And now let's look again. Let's go back because we need to do, I suppose I could just do a refresh here. Because it's going to be the same role, but it's going to be a new policy. So if I do a refresh here and look at the execution role, here's my execution role. I'm going to keep doing refreshes now because my browser might be caching. And here are the two policies again. And if we look at this policy, and here we can see now that the policy only has the three actions that I've defined manually, if you like, in my CDK code. And if I try to run my actual Lambda, does the Lambda still work? Is it still able to do the read all movies from the table? Well, let's see. So the path, as we know, is just /movies. And it looks like it works okay. Right. So the purpose of that demonstration was to show you that in your CDK code, you can write IAM policies and attach those policies to whatever service you want to. In our case, or attach them, sorry, to whatever resource you want to. In our case, we were attaching a policy to a role that was linked to a Lambda function. And as I also said, the reason I'm doing this is because that may be something that you will need to do in the assignment, albeit at the latter end of the assignment. Okay. Again, I'll offer the opportunity to ask any questions if there are any. No. Let's go back to the website. So at this stage now, I've kind of finished looking at the serverless side of this module. Although we're going to be looking at some other AWS services, which would also be categorized as serverless, but we're going to be looking at them from a different perspective. The next thing I want to look at is what I've titled application architecture. And if I go into this section, this is probably going to be definitely going to be the only section that only has slides, doesn't have a lab, because this is kind of theoretical. So you're going to have to try and stick with me if you can. It's always, I think, always a bit more difficult to stay in tune when it's just a purely theoretical lecture, but I'll do my best. So the slides that I want to walk through, let's bring them up. So application architecture. So if we roll back to 2011, isn't that long ago, then certainly at that stage in 2011, okay, the internet was still around for about 2 decades, I guess, roughly thereabouts. But it's a little bit like the kind of hype that's going on at the moment about AI and how AI is going to revolutionize businesses, and not just businesses, but broader than that. But back in 2011, there was an article written in the Wall Street Journal, which, would be kind of classified as a business type newspaper, I guess. And the title on the article was Software is Eating the World. And essentially the point that the author was making is that software, which admittedly now had been around for quite a while at this stage, it was really becoming central to any type of business or organization in order for that organization or business to function. And that was also kind of reflected in when you looked at the executive boards of these businesses and organizations. There was one person on the executive board, which typically had the title of the CTO or the Chief Technical Officer. And essentially that person, their responsibility was to look after the role that software played in the day-to-day running of that business or organization. It was kind of that, it was felt that important that it was now central. For a number of years prior to that, it wasn't considered a really important part of any business, their use of software to carry out whatever the nature of their business was. But from this journal, the author was saying that really, unless you utilize software in whatever aspect of the running of your business, then you're not going to survive as a business. And that has come to pass. You just cannot, you don't come across any type of business now where software isn't being used in various areas of that business. So we'll take that as read, that software is essential for the operation of any type of business or organization. And if we take that as read, then what we also hear a lot in the media these days is that businesses, they need to be agile or adaptable. And they need to be that way because the the market is very volatile. It's rapidly changing. It's a complex market. And so the businesses that operate within a market that is very volatile and very uncertain and very complex, the software that they use needs to be able to adapt to that changing environment. Yeah. So the businesses need to be agile. Software is central to any business. Therefore, the software that they use needs to be able to be adaptable and changeable very rapidly. And that's where the story kind of lands on our plate. We as software developers, we need to be able to deliver software, I'm saying here, deliver it rapidly, frequently, and reliably. Rapidly, as in, when a business comes to us and says, you provided us with an application 5 years ago, but we need to make a number of changes to that now because the business that we operate in, the environment, it has changed. So we as software developers need to be able to rapidly alter the software, adapt it to the new changing business environment. And that needs to be done quickly. It's something that we're going to be doing frequently. The days are long gone where you develop an application for a client and that does them for 10 years without ever needing to make any changes to it. So we're going to be constantly and frequently adapting our software for the businesses that use it. The reliability, obviously, the software, has to stay up and running. And invariably, that software now is running over a network, i.e., it's running in the cloud. And the cloud has additional problems related to reliability, as in, parts of the network go down, but we still want our software somehow to be available to our businesses so that they can still function. Here I'm just talking about, well, if we try to measure or quantify this idea of rapid, frequent, reliable development, if we try to quantify it for us as the software developers, there are two measures that you could use that are often mentioned in the software development world. We talk about the velocity of our software development process. And I'm saying here that velocity, there's a couple of ways that you can kind of measure the velocity of your software development process. One might be, what I'm saying is the lead time, which is the time from when you commit to let's say a GitHub repo. Let's talk in terms of software development. From the time you commit to a GitHub repo to that, whatever changes you made in that commit, to those changes actually being now run in the production environment, i.e. in the business environment. And we saw for those of you that attended my Agile module last semester, we talked a lot about CI/CD. So essentially here we're talking about your CI/CD. How finely tuned is your CI/CD process? Because that is what will determine how quickly you get from the stage of having some set of requirements that the business has put on you to include in an application, to adapt your application, how quickly you can turn those requirements into production ready software. Something like, obviously it depends on the size of the requirement. But if we just talk about the time between we commit to our GitHub repo and commits, let's say, are small changes, let's say for now, and those commits actually finishing up in production, really finely tuned CI/CD processes in very sophisticated software development houses, you may be talking about something like 15 minutes turnaround time. That's obviously a very high target to aim for, but it's that kind of frequency. We're not talking about weeks and months. That just isn't going to work, given what I've talked about up here. Another way is, another measure of velocity is how frequently do you actually redeploy your application, which is kind of the back end of your CI/CD process, if you think about it. And some of the stuff that we've been doing in this module is is relevant to this velocity kind of idea. But deployment frequently, the number of deploys that you do per day, deploys to the production environment now. And again, for very well-run software organizations, we could be talking about a number of deployments per day happening to your production version of your software. Another measure of rapid, frequent, reliable software development. Well, I'm just calling it reliability here, but okay, we may have a CI/CD process that allows us to deploy changes to our production environment very frequently, number of times a day. But obviously, if those changes are causing our production environment software to crash, that's not a good idea. But sometimes it will cause it to fail. And so how quickly can we actually fix those bugs and get those fixes into the production environment? That's also an indicator of how rapidly, frequently, and reliably you as a software house develop software. Okay, so there are kind of generic ways of quantifying how good a software house is at meeting the needs of the business that they serve. In this slide, I'm talking about any successful application. It tends to live for a long time. Now, I'm not quantifying what long means. It could be, if you get 10 years out of an application that you develop for a customer, that's probably pretty good, I'd say. But it does tend to live, successful ones tend to live for a long time, we're saying here. But we know that the whole technology area is constantly changing. And we'd like to be able to avail of the new technology changes, even in our long-running applications. We'd like to be able to adapt our long-running applications to avail of technology changes. And the technology changes may not have anything to do with adding new functionality. It's just having a better platform that our application runs on. Now, how can we how can we achieve that? How can we have it so that we develop applications that have a long life, but we are able to avail of changes in technology and utilize those changes in our long-running applications? Again, are there characteristics of our software development process, i.e., our CI/CD process, that will enable that? And in the diagram, it's being suggested that there are three things that you need to look at in your software development process, in your software development organization that can allow this here to be realized. It's the process that you actually use, which is the CI/CD part. It's the organization of your software people, and it's the architecture of your application. Now, we are particularly interested in architecture, but the other two are interesting to us as well. This is just an elaboration. So in terms of process, we would like to ensure that we have, these are different terms for the same thing, but we'd like to have a lean software development process. Lean is a term that's used a lot in the business world, not so much in the software development world. What lean translates to in the software development world is a DevOps process, which is a term you may have heard of. And DevOps is really another way of talking about the whole CI/CD pipeline idea. So any software house today anyway should have a CI/CD pipeline as a central part of their software development process, which is why we included it in that module last semester. Down here, in terms of how you organize the various software engineers that make up the group of people that are developing an application, it's felt that what you should try and aim for is to have subgroups of small teams that are autonomous. So the entire group of people that may be the entire group of software engineers that are responsible for maintaining an application, you could be talking about 20, 30 software engineers, obviously in the large scale. But if you can break that group of 30 software engineers up into small subgroups or small teams, where each team is responsible for one particular part of the application, and that team should be autonomous, meaning that they can make changes to their part of the application without affecting other parts of the application. That's the ideal scenario. And that's what a software house should try and aim for in order to satisfy what I spoke about on the previous slide. Architecture is what I want to talk about mainly in this set of slides, because how can you structure or architect an application so that if that application is a long-lived application, we can still avail of changes in the that are happening in the technology world and apply those changes to our long-lived application. Okay, so we're focusing in on application architecture. And here I'm saying, again, we're talking about how you measure or quantify things. If we want to be able to make statements about the quality of the architecture of an application, what are the quality attributes of a good architecture? And I'm listing them here. And again, usually qualities or attributes tend to be kind of a generic high-level ideas, although some of these are very tangible to us. In fact, all of them, now that I think about it. First of all, how testable is the application code? We know from the module in the previous semester, we like automated testing. We want to automate as much of the testing as possible. Now, is the architecture of our application, does it allow automation of testing to be carried out? I guess you would say today that's probably true of most applications, but it wasn't for a number of years. Number two, another quality attribute is the deployability. How easy is it to automate the deployment of your application, which is a lot of what I'm talking about in this module and a little bit on the previous module. The maintainability of your code base. Is it easy? And maintainability has two parts really. Is it easy to understand the code in your application? We're talking about large applications now, obviously. Is it easy for somebody, let's say a new software engineer joins the team, and you give them a task to carry out a particular change to a particular part of the functionality? Is it easy for them to understand the code that they need to study before they make changes to it? Is it well structured, et cetera, et cetera? So that's what maintainability really means. Easy to understand and easy to change. Modularity, always a good thing when you talk about software development. Is the application source code broken up into meaningful modules and modules that are kind of isolated from one another? It's easy to break code up into modules, but if there's a lot of if there's an awful lot of interaction between those modules, that's probably not great. But modularity here, I'm saying they should have impermeable interfaces. Each module should carry out one particular function, and its interface should be such that if another module wants that module to carry out its functionality, the API should be sufficient to allow it to do it. Evolvability, how easy is it to adapt your application for changes in technology or indeed changes in functionality. So these are the attributes that we like to maximize in our applications architecture. The other two down here that I'm mentioning are very important as well when your application is running over a network. The scalability of your application. Is it easy to scale up functionality to deal with peaks in traffic? Fault tolerance is, again, if your application is running over a network and part of the network goes down, does that mean that your application is just not available to the end user? We'd like that not to be the case. We'd like our application to be able to tolerate faults in the network. Now, we kind of know that the way you do that is by replicating the functionality around the network. But in general, these two characteristics are also key to a quote unquote good high quality architecture. Now, let's talk about specific architectures. And for a number of years, if not decades, there was only one architecture. And pretty much when I think about it, most of the applications now, okay, the applications that ye have developed are small, but in terms of architecture, it would be, I think, safe for me to say that the architecture that ye have used always has been the monolithic architecture. And we're trying to get away from that. But anyway, what is this monolithic architecture? I'm saying well, first of all, it's the traditional way of developing. We're mainly talking about server side. When I talk about applications here, I'm mainly talking about the server side of them. Okay, so for years, as I said, it was the only architecture available to us. And what are the characteristics of this monolithic architecture? You've probably heard of the monolithic architecture already, but just to be sure, as we say. The monolithic architecture, it's characterized whereby it has a single code base. It's deployed, the entire application is deployed as a single unit or a single package or a single archive onto a server, but it's deployed in its entirety as one unit. Now, if you think about, let's say, the web APIs that you developed in last year's web app dev module, okay, in terms of functionality, they were pretty small, but we deployed those web APIs as a single unit. Whereas a lot of the serverless stuff that I've been talking about so far, where we break the functionality up into lambdas, even though I didn't cover it, lambdas can be deployed individually, and you can make changes to a lambda and just redeploy that lambda, that particular part of the web API. You do not have to redeploy the entire web API. Whereas what you would have worked on in the web app dev module last year, because it was this monolithic architecture, you just deployed the entire web API as a single unit, even though you may have only made changes to one particular part of it. Now, the good thing about this monolithic architecture is it has been around for quite a while, like decades. And so there are lots of tools and frameworks that are well proven in the industry for this architecture. So, I mean, that's a good thing, obviously. They're well established. From a scalability point of view, we say that an application that adheres to this monolithic architecture, it scales horizontally. I'll show you what I mean by that in a moment. Here I'm saying that the code updates, whether that be a bug fix or adding new features, a code update requires an entire rebuild of the entire application and a redeployment of the entire application, even though the new feature may be isolated from all other features, or the bug fix may be related to one particular feature within the application. We can't just build that particular part and redeploy that particular part. We have to rebuild the entire application. Now, what I'm saying down here is that, okay, for small applications, then the monolithic architecture was fine. It satisfied all of the qualities that I mentioned back here, right? But only for small applications, though. Once complexity entered the picture, then that's where the monolithic architecture tended to break down. So there was a lot still good about it, even though certainly gets a bad press today. And most applications, large applications today, would not follow this monolithic architecture. But just to elaborate on the monolithic architecture in a kind of visual way, this is something that I just a screenshot that I found on the web, which kind of illustrates what I've been saying so far about it. So here's my application, and okay, it's broken up. It looks like it's broken up into nice, well-defined modules. These white boxes now would be the modules in terms of our modularity. Now I'm using the word service here, with the exception of the first one. I'm using the word service, or the image is using the word service. Service is a term that has only come into the software engineering space in more recent years. Back in the early days of the monolithic architecture, we didn't use the term service. But that aside, let's just call them modules. The module seems to be, they seem to be well defined and self-contained, but in terms of the architecture, all of these modules, these white boxes, they're all packaged as a single unit. Now, the unit, if we assume this is a web application, the packaging is referred to as a WAR file. Probably have not come across it. It's a little bit aged, but WAR stands for Web Archive. It's a type of archive. We packaged our entire monolithic architecture, our monolithic application, in a single WAR file archive, and then we deployed it onto a server that understood this WAR format. Now, a very popular server at the time was one called Tomcat. Like, I can remember, okay, we're probably going back maybe 15 years, but I can remember pretty much, maybe not all, but an awful lot of fourth-year projects would be using the Tomcat server and developing a web application, hopefully that had nice modules, but they were deploying it as a WAR file onto a Tomcat server. Typically, they were running the Tomcat server on their own desktop. We didn't have the cloud back then. But if there were any type of services that allowed you to run Tomcat remotely, then okay, they did that, and some of them did. In terms of scalability, the way we scale this type of application up is we essentially run multiple instances of our Tomcat server. And that's what I'm trying to get across here. That's how you scale up. So you scale multiple copies of the entire application across multiple Tomcat servers. And hopefully those Tomcat servers are running on separate nodes in a network. And those nodes are such that if one node, one part of the network goes down, that only affects a subset of the nodes. So your application is still available from the other nodes that the application has been deployed to. As well, the other point that I want to make is in terms of scalability, like it may be that it's really only the accountancy, let's say it's the accountancy part of my application that is experiencing high volumes of requests coming into it. But we still have to scale up entire copies of the entire application across other instances of my Tomcat server. We can imagine that new instances of my Tomcat server can be spun up on the fly. But the reason we would spin them up is because there was a particular part of my application that was experiencing heavy traffic. The other parts may not require scaling up to happen at all, but we still have to scale up. We had to replicate the entire application across the other servers. That's what we mean by horizontal scalability. Drawbacks of this architecture, well, as I kind of indicated, any successful application is an application that keeps, well, sorry, I didn't make this point. Any successful application I'm saying here is one that grows over time, as in your client or your business is asking you to add more features to the application. That's obviously a good reflection on our application. But if the application, if its sheer code base is growing over time, then that means that the development team that's responsible for maintaining the application, the team size is actually growing as well. And the larger your team size is, the more complications it introduces in terms of managing that team and coordinating that team and coordinating the changes to your code base, because your code base, we said one of the characteristics of a monolithic architecture is you have a single code base. We could think of it as a single GitHub repo that the entire team is contributing to. And, there are obvious uh, reasons why that does complicate things in terms of managing and coordinating code changes. GitHub helps, of course, and the kind of GitHub pull requests model, all of those things help. They haven't been around forever though, but still, there's a lot of extra headaches associated with your development team growing and growing over the years. Modularity, I'm saying that tends to suffer as well as your application's sheer size tends to grow. The modularity tends to break down a little bit. And so, whereas on that picture that we had a couple of slides back, we had nice, clean white boxes, but over time, those boxes tend to overflow into one another, if you like, and so the modularity breaks down. And if your modularity breaks down, then that has a knock-on effect on maintainability and testability. And moving on to number 5, I'm saying your technology platform. Oh yeah, yeah. Your the platform that your application is built on. Technology, as I said a while back, is evolving all the time, and so your technology platform tends to become dated. And that's another complication to, albeit a successful application that's growing over time. It's now running on old technology. Okay, so monolithic, great for small applications, not so good for very large applications, and certainly for large applications that are successful, i.e. they live a long time because for the reasons that I've mentioned. This is just kind of visual of or a diagrammatic representation of what I've been saying on the previous slide or two. As your application's size grows, what this arc is representing, the quality attributes, testability, maintainability, etc., they tend to deteriorate or get worse, whereas we'd like them to improve with the growing size of our application. So enter a new architecture that emerged around 2011, 2012, which happens to be the same period that Wall Street Journal article came out, but that's just coincidental. I'm just checking my watch. Oh yeah, okay. So the microservices architecture was really an architecture that tried to address the drawbacks associated with the monolithic. Surprise, surprise. What does the microservices architecture? And again, you may have heard of this from your own readings. So I'm saying the microservices architecture is an architecture style that structures an application as a set of services. Now, it's only when the microservices architecture, when that label was put on this new architecture, it's only then that we started using the term services when we talked about software. Okay, I used the word service on this image here, and I explained that really that term wasn't being used at all when this monolithic architecture was actually was kind of popular. But so the microservices, I'm saying it breaks your application up into services. Now, how is a service characterized? It's not just a module, it's much more than that. I'm saying here that a service is characterized in the sense that it's organized around a single business capability. Well, we had that on the monolithic architecture. So this first point here doesn't really distinguish microservices architecture from the monolithic architecture. You could still achieve this modularity, really. You could still achieve this with the monolithic architecture. But what was unique about the microservices architecture is more these points here, right? That each service could be independently deployed and scaled. And also each service was owned by a small team, a small autonomous team within the overall group of software engineers, which was one of the points in that triangle that I showed you a good few slides back. So each microservice could be deployed in isolation. Each microservice was owned by a small subgroup within your overall software engineering group or a small team, and that team that was responsible for a software service, at least in theory, they could make any change they want to their service without impacting on the other services. Now, that was the theory, although that kind of broke down as well eventually. But let's assume the happy path for now. Each service was highly maintainable, mainly because each service now is a small part of your overall application. So there's less physical code, and we know that maintainability is about the understandability of your code. And clearly, the smaller the code base, the easier it is to understand it and to test it. Okay, so this is really more linked to the volume of code. It's kind of a visual representation, and I'm using the same functionality blocks here as I had in the monolithic case. But what we now need to take from this, though, is that each of these boxes now, each of them runs on their own, in their own environment, which really means that they run on their own VM, let's say. Now, each of these boxes, it's not as big as its own. It's not as big as an EC2 instance, to use the Amazon resources kind of terminology. It's not an individual EC2 instance. It's smaller than that. It's not a Lambda either. It's bigger than a Lambda. It's really kind of a container instance, i.e. like a Docker image instance, for those of you that might be familiar with it. But if you're not familiar with Docker, then just treat each of these boxes as a piece of functionality that runs on its own VM, on its own hardware server, let's say. And if it needs to communicate with other services, it's doing it over a network, over HTTP. Each of these boxes now can be scaled up individually in isolation. So that solves the the scalability constraints that we had with the monolith. Each of these services is much smaller than an entire application. It's just part of an application. So the team that is responsible for managing this service, they can make changes to it, improve the performance of it, fix bugs on it, add features to it, and redeploy it and do it without necessarily being concerned about the other services. At least that was the theory in the early days of microservices, but that kind of broke down. But that was the idea anyway. Also, what's kind of odd is that each service, the idea anyway, was that each service had its own local database. So there was no shared database, which was the case. If I go back to here, right, it was the same database that was being used by each of my modules. So the database tended to become a bit of a bottleneck. In the microservices architecture, and a lot of people had difficulty with this in the early days of the microservices architecture, each service had its own private database. That really meant that the information that might be stored in the database, then maybe some of it had to be replicated. So you might have, let's say, user related information in this database and more user related information stored in this database, and you had to kind of keep them in sync. So that was a complication that was added in as a result of having multiple databases. But the reason we had multiple databases was to avoid the kind of bottleneck associated with the database in the monolithic architecture. Okay. Does it satisfy these various quality attributes? Maintainability, I've already made that argument because each microservice, we call each of these now a microservice. Each microservice is more maintainable than a monolithic architecture due to the volume of code. Better modularity. Each microservice now is a module, if you like. Better testability, all of that good stuff. The other thing was in terms of evolvability. Like this service here, it might be implemented in Java, whereas this service here might be implemented in Python, and this service might be implemented in TypeScript. That flexibility was completely available to the team that was responsible for a service. And also, the team that's responsible for this service, they may decide that they want to add a new feature or fix some bugs. And they may do multiple redeployments over a period of, let's say, 6 months. Whereas the team that is responsible for this service, they may only do a small number of redeployments over that same period. But the accountancy team, because this microservice is running and it's independent of everything else, they're free to decide how frequently they want to redeploy. And they're free to decide the kind of new features and the schedule that they come up with for implementing those new features. They don't necessarily have to consult with the rest of the teams. Again, I qualify that by saying at least that was the theory in the early days of the microservices architecture. So evolvability was the evolvability characteristic, we could say, was very high for this microservices architecture for the reasons I just gave. Also, its testability is much easier because we can now test each microservice in isolation, and we like that. Deployability, I've already made that argument. Better scalability, I've made that argument as well. I think I have anyway, that, if let's pick another one. Let's say if the marketing service is suddenly experiencing very high volumes of requests coming in, then we can scale up if we think in terms of AWS, AWS can dynamically scale up or in other words, make multiple instances of this service and scatter them across a range of servers dynamically, whereas the other services don't need to be scaled up. So we can be more granular in terms of scalability. That type of scalability where you scale a particular part of the application is the opposite of horizontal scalability, and it's called, surprise, surprise, vertical scalability. Fault tolerance, it's kind of the same argument. Let me just clean that up. If the node that this service is running on, if that node is certainly inaccessible from a networking point of view, because these other services are running on different nodes, then they may not be affected as a result. So here, the benefits, well, as a result of improved modularity, improved testability, improved maintainability, et cetera, they all mean that our process is better, and better means we can deliver new features rapidly, frequently, and reliably. Okay, so our process is improved. In terms of the organization of our software engineers, because we now assign each microservice to a small team that can evolve that service independently of other services, then we kind of satisfy this objective down here. So it looks like the microservices architecture aids our process and also aids our organization. The challenges associated with the microservices architecture, complexity. Complexity always adds difficulty. Complexity in relation to microservice architecture, though, is more related to, the kind of communication, because the services are still going to need to communicate with each other, but now they're communicating across a network, and that adds another layer of challenge because the network can be faulty. We can have what are called partial failures. So if one of my services, in dealing with a request that comes in from the client, if it needs to communicate with another service, but that service is down, as in it's inaccessible, then what do we do? How do we handle that scenario? It's hope it's temporarily down, but how do we deal with that? We have to somehow programmatically deal with that issue. That was not an issue in the case of the monolithic architecture, because any communication that happened between the services, because all my services ran within a single operating system process, then all of the communication was synchronous. So we didn't have this inter-process communication, partial failure complication. Distributed data, that as a result of this multiple database thing that I was mentioning. Testability, you see, the new thing now is that end-to-end testing was now challenging. By end-to-end testing, we mean from, let's say, for a particular request from the client that goes to my gateway, maybe initially it hits this service, but this service has to communicate with this service, and this service has to communicate with this service in order to complete the transaction. How do you automate the testing of those types of requests? Okay. Today there are frameworks that help us with that, but in the early days of the microservice architecture, end-to-end testing was an issue that could not be automated. But as I said, there are tools that allow us to do it now. And deployment, even though I'm painting it as a very kind of rosy picture, the whole deployment and redeployment of services wasn't really as straightforward as I made it out to be. Because, for example, if let's say I want to do a redeployment of this service here, and as the redeployment is happening, a request comes in to my application, it hits this service, and this service wants to communicate with the accountancy service in order to complete the transaction. But the accountancy service is currently going through a redeployment, albeit that the redeployment may take moments, but still, it's still going to be inaccessible for that brief period of time. So it's not as rosy as I might have indicated. What are we saying here? Refactoring. Well, so when the microservices architecture came into being and started to grow in popularity, then software houses started to look at, well, how can we take our existing applications that adhere to the monolithic architecture, and how can we migrate it into a microservices architecture? So, there's kind of do refactoring. Now, there are strategies available to us today. A very popular one is the one called the strangler pattern, or the strangler strategy, as to how you go about that. But again, in the early days of the microservices architecture, and once it started to become popular, this was one of the issues that software houses were trying to address. Down here, I'm talking about correctly identifying the service boundaries. Again, I've kind of suggested, that the service boundaries are very much aligned with business boundaries, like accountancy and inventory. These are all typical business departments, if you like. Do we necessarily break our software services up in line with the departments in a particular organization? Maybe, maybe not. And what 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 was arising with this issue here of how do you break up a monolithic architecture up into microservices such that each service is is isolated from other services. What if you don't do that correctly, then what was happening was you were finishing up with what was being referred to as um, the microservices monolithic architecture. So you kind of had the worst of both worlds. And a microservices monolithic architecture, how that is characterized is like this, where there is an awful lot of inter-service communication going on. And this is a reflection of an applications architecture that has been broken up into the wrong set of services. And if there's too much communication going on between the various services, then that may be an indication that you haven't actually broken the monolith up into the right set of microservices. Okay, let me just check my watch. Sorry, just give me 1 second. Sorry. Right, where are we? Coupling. Okay. Now I appreciate this is kind of heavy going, so I think what I'm going to do now is I'm actually going to just stop here and pick it up and finish off this set of slides with you the next day, because it is heavy enough going, I appreciate. So where we're at now is we know what microservices architecture is at a very high level. We know the characteristics of it, but we're starting to see that while it satisfied a lot of the problems associated with the monolithic architecture, it also introduced some kind of new problems. And I'm mentioning some of them here. Because the complexity issue, the refactoring, the migrating a monolith back to or migrating it forward into a microservice architecture. And finally, how do you actually decide what are the service boundaries of your microservices architecture, such that you don't finish up with this microservices monolithic anti-pattern, as it's called. An anti-pattern is something that we try to avoid. Okay, I am going to halt it there, and we'll try and pick up the story from there next week with you. Okay, I'll leave it at that. Thanks. Bye-bye.